Bom dia. I will start now. My name is Timo Drick. I'm Android developer at 7 Principles, and I will demystify pixel shaders today. I live in Frankfurt, in Germany, and I'm Android developer full-time since 2010. And now, I give you a short introduction to shaders, what shaders are. By the way, there's a QR code, and you can scan it, and there are all slides, so you can watch the slides also in the net. So I give first a short introduction to shaders, and then I will show you how to use shaders in Compose. And then we go a little bit more into details of shaders, how to draw shapes with shaders, and then later animations. And I will also show a little bit more about how you can develop shaders and how it works in the engineering process. And then I give a short summary. So let's start. First, some samples. What can you do with shaders? So here you see a normal app, and the background is drawn by a shader, this triangles and this light things. And here's another example of this wave lines in the background. This is also drawn by a shader. Here's another background. This is one of the sample apps of the Android Google developers, this sample Compose app, Jetpack. You find the source code also. By the way, all the samples I show you today, the source code is available. When you look into the slides, there are links, so you can find everything. And when you look closely here, the background is also animated. You can also, for example, animate your buttons with shaders. The shine animation is done by a shader. So maybe when you have a button which you want the user to click or at least get the attention to, then you can do some animations here. Or you can do loading animations like this with shaders. Also maybe, you want to program in AI. I think everyone does this today, right? So, but how can you visualize this AI? You can also use a shader for this. Anyone knows, recognizes animation? Which AI could it be? Yeah, okay. I learned that someone does not know Kit, so it's a series from the 80s, I think, with David Hasselhoff, so maybe you can Google later for it, But the older guys know this. We can also go crazy with shaders. For example, you can make the button really hot, so maybe the user touch it or do not touch it. Or you can also do the 3D stuff with shaders, Or also transition animations like this certain animation. So when you want to a transition between one composable to the other. So let's talk a bit about the theory. So shaders are almost used in every graphics pipeline nowadays. So even the very old Android devices do have graphics cards inside. And today my talk is about AGSL. It's Android Graphics Shading Language. And it was introduced in Android 13. And the new thing now, what you can do with it is create custom shaders. Shaders are also used in games a lot. And normally you know it from OpenGL and Metal. And Metal is this OpenGL from Apple. They have their own standard for macOS and iOS, and of course also WebGL. One important thing, the code of the shaders will get compiled and executed on the graphics card. So it's not the same like Java or Kotlin code. It's very fast. But we will see. So maybe you also know how to draw something with Compose, or also with the legacy view system. By the way, everything with shaders today, it works also with the legacy view system, but my samples are only for Compose. So for example, when you want to draw a circle with the normal draw canvas API, then you can fill it with a solid color, or you can use a linear gradient, yeah, which is also one type of shader, yeah. Very simple one, of course, or a radial gradient, or you can use an image as a texture for the shader. But today we will have a look at the custom shaders. And yeah, unfortunately, it's a complete separate language. It's not Kotlin or Java. So you have to learn a new language. It's similar, it's like C, some kind of C. But yeah, as you can see here, we define one main function. And this function gets as an input the coordinates of a pixel on the screen. And it has to return the color. And that's all. So it's very simple. You just get x, y coordinates of the pixel on the screen, and you return the color. And the graphics card will then run this function in parallel for every pixel on the screen. It depends, of course, on how large your screen is. And you return an RGB value, so for red, green, blue, and an alpha channel. And yeah, as you maybe already noticed a little bit, we do have here this float 4 and float 2 types. And it's kind of a vector or yeah, an array in Kotlin or Java. So this means here there are two values inside of this fraccord variable then. So and the first one is x and the second one is the y. And the return value is a float of 4. And there you specify the red, green, blue channel and the alpha channel for the color. And yeah, here it's 1.0 is a full value. It goes from 0 to 1. So in this case here, it's red. So for the red channel, it's full. And for the other channels, it's 0, so no color. And the alpha channel is 1, so it occupies the background. And then the result would be this just red rectangle. Yeah, very boring. But it will get better. So for example, let's assume that this rectangle is exactly 200 pixels in width. And now, for example, when we want to do a linear gradient, we could divide the actual x coordinate from the pixel by 200. And then this value would go from 0 to 1 from the left to the right here. So here again, the data types. So this float 2, you already see. So you can directly access the different parts from this with .x and .y. There's also float 3, then you get the z for this. And for this alpha channel, you get this .w here when you use a float 4. Yeah, for colors, x, y, z is not so good, but you can also use RGB and A to access the components. It does not make a difference, so you can do it how you want. Okay, so now how we can integrate this in our Compose app. So here we see as a string the shader code. So you just can create a string. And when you use this add language annotation here with AGSL, then you get also syntax highlighting from Android Studio. So it then looks a little bit nicer. And And when you have the string here, you can create a modifier to show your shader. And here I use this draw with cache. This is not a new API. This is just the normal Compose API for drawing on canvas. The new one is this runtime shader here. This was introduced in Android 13. And you give the shader source as a parameter to the constructor. And then you can create a brush out of it. And this brush you can then use in your draw method here. And in this case, I just draw a rectangular with this brush. When you do not provide any parameters for the rectangle, then it will fill the whole screen or the size of the canvas. And yeah, here it's the code again. And then when you want to integrate it in a composable, like your screen, then you can create, for example, a box and add this background shader modifier here. And then the output would look like this. Yeah, still a little bit boring. It's just a red background now. But we are able now to change the shader. So now maybe, I showed you this linear gradient with the 200 pixels width, but you don't know how the width of your rectangle may be. So we can use uniforms to transfer some data from our Compose code to the shader. And here's an example to get the size of our canvas into the shader code. And here you see in line 2, I modified the shader code, so it gets here a uniform float 2 size. And I use this size then here. And in the Kotlin code, you can just use this shader set float uniform. And then here the name, of course, the size must match the variable name inside of your shader code. And then you provide the 2 floating point values. You can also use float 3 or 4, then you have to provide more parameters here. And yeah, then I modified the code a little bit, so it will the x coordinate will be divided by this the width of the canvas. So then the linear gradient will adapt to the width of your view. Okay, so next topic. It's a little boring just to do some linear gradients or something like that. Maybe we want to draw a little bit more shape. So for this, because we get the pixel coordinate and need to return a color, it's not possible to just have some methods like draw a line from point 1 to point 2. We have to do everything, the math from scratch on our own. But it's not so complicated because at the end we just need a distance function. So that we know when we have the coordinates of the pixel, where we are, we need to know the distance to the shape outline. One simple sample is just using a circle. And the distance to the circle is just the vector distance between 2 points, or the length of a vector. Fortunately, in the shader language, we do have a function for this already built in, and it's called length. And we have to provide a vector to it. And to calculate the distance, we just subtract the position from this coordinate. And in this case, I want to draw a circle at the center of this canvas. So I use now, let's assume the canvas is exactly 200 by 200. So my circle will be at position 100, 100. And now I can calculate the distance by just subtracting the circle position, so this is the midpoint from the coordinate. And so that it's not a tiny point, I subtract the radius of the circle, and then I get the distance. So this is this d value. And now to calculate the color, I can just check if it's smaller than 0 or bigger than 0. And depending on this, I use white or black in this case, but of course you can use any color. And just return it. Sorry. Maybe one thing you notice here, the edges of the circle are very pixelated here. Yeah. It's not an error from my slides, or that's a bad resolution here. It's because of this function. And to get rid of the pixelated edges, we can use a smooth step function. This function you get, you provide a starting value and an end value, and the input value itself, and then it will return a value between 0 and 1. But it's not linear, so it will, at the beginning of this range, so you provide a range starting and end, and at the beginning of this range, it will slowly start to increase, and then later at the end, it will also do a smooth transition. Other thing we need is the mix function, so that we can mix two, you can mix anything, but we want to mix two colors together, so the background and the foreground color. And this is just a linear function between both values. Here is the mathematical function, but it's not so important that you know it. This mix function is also built in the shader code. And depending on the value you put in at this weight, it will completely use the component from A or B. And when it's between, for example, 0.5, then it will exactly mix both 50% by both parts, the color. And now we can change our code here. So first, here I introduce this smooth step function. And here I created a variable s for the size of this edge. And then in the smooth step function, I go from 0 to s and provide, and d is the actual value. Yeah. I have to subtract s from the radius, because otherwise my circle would be greater than the canvas and it would not fit here. And then I can mix the foreground and background color based on this smooth step function. Yeah? And here you see it's now very blurry, the edge, because I used 20 pixels as the range between, or as the size of the edge. Of course, I can now change the size. This is even bigger, then it's more blurry. And you can also reduce it. And then here you see it's not pixelated at the edges. Still a little bit blurry. You can also reduce it more, but then it gets pixelated again. So you need to try a little bit which value you need. Okay, so that was a circle. And of course, maybe you do not want only to draw circles. So you can draw different shapes. Here you see a rectangle, a triangle, or a hexagon, or a pie chart, something like that. And a great source to get these functions, the distance function for the different shapes, is from Inigo Keyless. And the link is here. As I said, everything is in the slides. Yeah. Okay. Now you know. I mean, in this on this page there are many more shapes. So it's just I just have provided some samples here. Yeah, there are more. And now maybe we want to combine different shapes together to create more advanced shapes out of it. So the good thing about this distance functions is that it's very easy now to combine different shapes. Yeah, for example, when we want to subtract two shapes from each other, here two circles, then we just use the maximum of the distance of both, but provide a minus here for the shape you want to subtract from the other. And union is also very easy. So when you combine two shapes together, here, this as example, then you just use the minimum of both distances. Also, intersections is easy, just the maximum without a minus here. Yeah, we can do other things, some kind of deformations, and yeah, and instead of changing the distance formula or the values from the shapes, we can deform our coordinate system. So, for example, when we want to move the shape for just in x and y coordinates, we can just add a vector to our coordinate system. Or when we multiply it, then we scale it. For example, here I move first my center point, my coordinate system, I move it to the center. So I subtract 100 by 100. This means that here at the center it's 0, 0, and at the left it will be minus 100, and here plus 100. And then I can multiply it here by, now for this, the x component, I use 2. This means that it will be stretched, yeah? And when we change it and multiply the y coordinate, then it will be shrink down here in this, and the width will stay the same. We can also rotate our coordinate system. I will not explain this formula, but maybe one important thing here, you notice a new data type, a mat2. It's a matrix, so it's 2 by 2 matrix. And you provide here an angle, and then you have this formula, and you get back a matrix, and then you can multiply this matrix by your coordinate system, and the coordinate system is then rotated. And now it's a little bit boring to rotate a circle because you will not see anything. So here I introduce a new function which creates just a rectangle. This is from this article from Inigo Quiles, so you can just look onto the web page from him. And I do the move the center position again here, the coordinate system to the center. Then when we want, for example, to rotate our rectangle by 45 degrees, we have to do a little bit of math because the angles must be provided in radians. So you can use this formula, or you can directly provide it in radians. And then, as you can see, I just multiplied my coordinate system by this matrix. So this rotate will return a 2 by 2 matrix. yeah, and then, in this case, I also use the smooth step here to smoothen the edges a little bit and mix foreground to background. So now, still maybe you're thinking that's boring. What can I do with this? I want to show you one example now. Here, this is just using this function what I already showed to you. So it's just triangles, different colors, and smooth step function. It looks a little bit boring with this beamer here, but yeah, normally it's more smooth. The code for this is also, it can also provide you. Here I defined a triangle function. Also, I use this triangle function from Inigo Keyless. And I have here a rotation so that I can provide different parameters for rotation and the smooth step factor here. And then that's all what you need to create this background, for example. So it's just 31 lines of code. Okay, next topic, animations. How can we do animations? So let's create an animation shader. So first the compose code. In this case, I need some variables from compose. So in this case, the modifier, I use compose keyword here. So I can introduce here an animation variable from compose. So I use this infinite, I use this remember infinite transition and then create an animated float out of it. You can, of course, use different methods to create your variables, but for me, it's now the easiest to do it this way. So I just create a variable which gets a value from 0 to 1. And also important that you define this animation specification, that it will be, you can define the duration. In this example, it's 2 seconds. But important is this linear easing, because otherwise the time gets distorted. So for me, in my shader, it's easiest to have a variable between 0 and 1, because it makes the math much easier. And it's not distorted. So you already know this uniform thing. So now we provide also a uniform for our time. It's iTime, and it's just this animation value. Compose will take care of everything and will refresh this variable on every frame of your composable. And here you see the code from the shader. Yeah, it's almost the same like before, but now I have this uniform iTime here, and I calculate an angle out of it, and in radians, 2 pi is 360 degrees, so I multiply it by 2 pi, and I use this minus because when you deform the coordinate system, it works all in reverse. So when I rotate clockwise, then it will, when I rotate the coordinate system clockwise, the shape itself will be rotated anti-clockwise. So I have to invert everything. Was still boring, but when we now play around a little bit and do a little bit more rectangles and not only one, we can get maybe a loading animation in this case. Here, this first line is to scale our coordinate system to values between -1 and 1, because then I do not have to change my shader code when the canvas size changes. So it will be scaled automatically. Here you see the angle calculation is the same. And now I use a for loop to draw many rectangles in this case. One thing to notice here is that in AGSL you cannot use any kind of for loop. You have to provide a constant value here as for this end point of the for loop. So yeah, you're a little bit limited. It's because it's backward compatible to very old versions of shader or of hardware, so it will work everywhere then. But yeah, as you can see here, I play around a little bit with these angles and rotate it. But I not draw directly the rectangles with this angle, but I just move the rectangle out of the center point a little bit, and then I use the angle to define an intensity, and use this intensity for my box, for the size of the box, and also for the smooth step. Yeah, and then I add all together. I also here, I clamp the values, so between 0 and 1. You can return values greater than 1 for colors, but yeah, then you get sometimes weird results. So in this case, I do not want it, so I clamp them, and then here I would return it. Yeah. Okay, one other animation, I showed you the shine animation, and here you see the code for the shine animation. It's a little bit simpler because I do not need to rotate my coordinate system. I can just deform it a little bit by, for example, here for my position, I add to the x coordinate, I add a factor of the y coordinate, and then it will be a little bit distorted to the right. And here I just use two smooth step functions for the starting edge of the shine animation and the end of the shine animation, and I subtract then the end. So I get brighter colors inside of this. Yeah, and then this is the same code. I use this highlight also for the alpha channel. This means that at this parts where the shine is not drawn, the background will be drawn. And yeah, I showed you this animation earlier. And now when you look closely, you see that's just rectangles and circles. So every one of you should be able to create it on your own now. Of course, the source code is provided if you want to see it, but yeah, in theory, you could do it on your own. Of course, you have to friggling a little bit around with the different variables and functions. Here's the code, by the way. It's very nice because it's just 31 lines of code for your shader, and that's all what you need. You don't need any libraries or something like that. Okay. Yeah, it's getting late. Now, how can we develop shaders? Problem when you you can change directly the code in your string variable, but every time when you do a mistake, then the app will crash. So it makes sense to catch errors during the development process at least. And then when you use it in Android Studio, yeah, you can just change your code. Here's a recording where I change it now. And here on this side, you see the preview from Android Studio, and here it's from the app. It's a running app on a device. And as you can see, when you have live editing on, when you change values here in your shader code, this is just the string variable, then it will instantly also update on on the device and also in your preview of your code. So it works also in preview. It's very nice. And for example, also animations work on the device. But on the preview, you see there's no animation. But in theory, animations work in preview, but it will not start the animation automatically. So I have to do it manually. I can click here and then click on play. And then it will also animate. But when you change the code, it will stop again. So it's a little bit disturbing. When you do animations, maybe it's easier to use a real device in this case. Yeah. Here now I changed the alpha channel. And you can see now the background behind this. Okay, so some words about compatibility. I already told you that, yeah, it's introduced in Android 13 or API level 33. So, yeah. Well, yeah, you need to make sure that your code is then executed only on devices which are newer. It's also supported in multi-platform, but there's a little bit different API, but the shader code will be exactly the same. And one important thing, AGSL is based on SKSL, and SKSL, it's Skia shading language, and Android uses Skia to draw everything, to draw lines and buttons, everything on the UI. Also, this legacy view system uses Skia. It's a drawing library, a C-based drawing library. And Skia itself do have this SKSL. So Skia itself uses OpenGL to draw everything. And OpenGL has this GLSL, OpenGL shading language. So SKSL is based on GLSL. And this is supported on almost all devices, also very old devices. This is an important thing here. So when you want to provide backward compatibility, one thing could be just provide maybe a solid color as background in case when the version of the operating system is too low. But in theory, you could also use OpenGL to draw your shaders. Yeah? I'm working on some kind of wrapper around OpenGL so that you can use the same shader code I provided to you in an OpenGL shader. But there are some limitations. You cannot then use it as a modifier. But then it will also run on very old devices. So when it's very important for your app to show a shader, then maybe you can use this. Or maybe you have to yeah, it's just a prototype, so yeah, you have to maybe fix some problems when you get something. Okay, so that's all. Now I will show you some more ideas what you can do with shaders here. For example, yeah, it's a pie animation in 3D, and it's also drawn by this AGSL shader. And when I move the device, the attitude of the device, when I turn it, then the shadow, for example, turns also. Another sample would be when you create an audio app, then you can draw this histogram by shaders. And you know what's this? How it's called? No, but this mascot from Google, how it's called? You don't know? Bugdroid. Yeah. Okay. Yeah. It's also simple shapes. Yeah. It's just circle here, half a circle, and yeah, here it's also some kind of circle. But you can also do it in 3D. And yeah, this is also AGSL code. Yeah, it's of course, a little bit more complicated to do it in 3D. I will not go into details now, so we're running out of time. So just a short summary. So you can create amazing effects with AGSL. And when you use it, it's not used a lot currently, so your app will really stand out. But of course, yeah, it's a very steep learning curve, so you have to learn a new language, and also, yeah, it's mentally a little bit different than drawing normal lines and using coordinates. So you have to use a different mask. But it's very fast because it runs directly on the GPU and in parallel for every pixel. But when you just want to draw a circle or simple shapes with lines and do not want this gradients and smooth transitions, then maybe it's easier to use the draw calls from the normal Canvas API. Here are all references and source code samples. As I said, it's everything in the slides. You can look it up here on this web page, or you can scan this code. Okay, so obrigado for your attention. So, yeah, do we have?